There are many ways to write an optimization problem. And actually, algorithms usually have a specific requirement about how you should write your optimization problem. For instance, some optimization softwares are designed only for minimization problems, not maximization. So therefore, you often need to transform the problem that you have written into a form which is acceptable by the algorithm. In this video, we will see some simple transformations that you can use in order to do so. Before doing that, let's clarify what we mean by two problems being equivalent. So we have two problems, the one that you have written and the one that you should submit to the algorithm. And we will say that these two problems are equivalent if you can create a feasible point of one of the two problems from a feasible point of the other problem. And these two should achieve the same value of the objective function. Let's take an example. Let's consider the problem P1, which is the minimization of 2 minus x, such that x is non-negative and x is less or equal to 1. And consider the problem P2, which consists in maximizing y and then change its sign, such that y is greater or equal to minus 2 and y is less or equal to minus 1. Now, if I want to consider a feasible point x of P1, in order to obtain a feasible point y of P2, I need to write y equals x minus 2. So for example, if x is equal to 0.5, then y would be equal to minus 1.5. And you can verify that x is feasible for P1 and y is feasible for P2. Now the objective function for P1 is equal to 2 minus x, which is 1.5. The objective function for P2 is equal to y, which is minus 1.5, and you change the sign, so it's also 1.5. So now try to solve these two problems and compare the two optimal solutions in order to check that these are indeed equivalent. The first transformation consists in modifying minimization problem into a maximization problem, or the other way around. In this picture, suppose that I would like to minimize the function f of x here. The solution, the minimum is x star, and the value of the function at x star is f of x star. So more formally, we can write that x star is the argument of the minimum of f of x, and f of x star is the minimum of f of x. Now, if I want to look at it from a maximization point of view, what I need to do is to change the sign of the function. So I will look at the function minus f of x. So this is the function which is plotted here. It's minus f of x. And now I will maximize it. And what we will obtain is that the solution, the x star, is exactly the same. And the value of this optimum, of course, has a different sign. So this is easy. If I have a maximization problem and actually I want to use a software that minimizes the function, I just change the sign and the optimal solution will be exactly the same, and the optimal value will be with a different sign. In optimization, if you add a constant to the objective function, it doesn't change the optimal solution. In this example, assume that I minimize the function f of x. The solution is x star, and its value is f of x star. Now consider the function f of x plus c plus a constant. From a geometrical point of view, this function is actually shifted above or below depending on the sign of the constant. But if we look at the minimum of this shifted function, we see that the optimal is exactly at the same place. And in terms of the value, we obtain the optimal value of the other problem shifted by c. So basically, if we have constant terms in the objective function, we can safely ignore them. It will provide the same optimal solution. Now suppose that I have an inequality constraint that is g of x greater or equal to 0. So it means that the set of x that are feasible are the one corresponding to this part in blue, so this section here and this section here, because for these values, the value of g of x is positive. But now assume that the optimization software that I'm using requires that all inequality constraints are less or equal. Well, in this case, what I have to do is to flip the function around the x-axis by changing its sign. So here I have plotted minus g of x, and the constraint g of x greater or equal to 0 is equivalent to minus g of x less or equal to 0. And we can see that we have exactly the same set of feasible solutions. So that's very easy. Now let's consider the case where my problem has an inequality constraint, but the software that I'm using requires only inequality constraints. So in my problem, I have a constraint which is, let's say, g of x equals 0, and I would like to write this using inequality constraints. But this is easy, so this is equivalent to the fact that g of x is less or equal to 0 and g of x is greater or equal to 0. Indeed, if these two constraints are verified together, it means that g of x is equal to 0. And if my software requires only inequality constraints which are less or equal, I can also write these two constraints. Most real problems in optimization are associated with variables that must be non-negative because they represent a physical quantity. Therefore, a lot of softwares actually impose this by default. All the variables which are involved in the optimization problem are imposed to be non-negative. But sometimes we don't want that. Take, for example, the temperature. We would like to optimize the temperature, but a temperature can be positive or negative. So it means that in our problem, we have a variable that can take any real value, while in the software, all variables must be non-negative. X belongs to the set of real numbers, and what we do is to include two new variables. One that I call x plus, and one that I call x minus. And I will define x to be x plus minus x minus. And I will impose x plus to be non-negative and x minus to be non-negative. So this is nice because now I have these two variables, x plus and x minus, that must be non-negative as required by the software. But then the sign of x itself, depending on which of these two variables is the larger, can be positive or negative. So in my problem formulation, I will replace all occurrences of x by the difference between x plus and x minus. So because this non-negativity constraint is usually implicitly assumed by the softwares, it's sometimes useful to translate the variable. And this happens when you have a constraint such that x must be greater or equal to a value a. In that case, you can make a change of variable. X equals x tilde plus a, okay? And in this case, this constraint becomes x tilde greater or equal to 0. Okay, so thanks to this translation, the constraint, which involves the data a, is now simply x tilde is non-negative. The next transformation is really an interesting one that we will use a lot in our algorithm. It consists in transforming an inequality constraint, let's say g of x less or equal to 0, into an equality constraint. And there are basically two ways to do so. The first one is when g is linear, and we would like to keep the linearity. And the second one is in the general case when g is nonlinear. So let's start with the nonlinear one. The idea is to include a variable which is called a slack. The slack will measure the distance between the value of g of x and 0, which is the maximum value that this g of x can take. And so we will write this. So we will include this variable z that will represent this distance, but z must be positive, so we square it. So g of x plus z squared must be equal to 0. So if z is equal to 0, it means that g of x is equal to 0. In this case, we will say that the constraint is active. And if z squared is strictly positive, it means that g of x is strictly negative. So we have the equivalence between the two. Now, if g of x happens to be linear, then we cannot use z squared because z squared is a nonlinear function. So the way we deal with it in the linear case is to say, well, we add also a slack variable, let's call it y, that basically does the same thing as z squared in the nonlinear case, but then we need to impose to y to be non-negative so that it makes sense. Okay, so in this case, we cannot really transform completely the inequality constraint into an equality constraint. But what we can do is to write it as a non-trivial equality constraint and a non-negativity constraint on the slack variable. So in this video, we have seen several simple transformations of an optimization problem into an equivalent optimization problem. These are valid transformations, and I encourage you to try it yourself on some examples to understand better how it works.